Hi everyone, my name is Etienne PUYOO. I'm working as an associate professor at INSA de Lyon. I'm doing my research activities in the field of flexible electronics within the Electronic Devices group of INL, Institut des Nanotechnologies de Lyon. Today I'm going to present some work related to the development of a portable device which integrates an ultrasensitive mechanical crack-based sensor for the wireless monitoring of cardiac activity. This work has been carried out in the framework of a project called PulseSensor in collaboration with colleagues from the biomedical sensor group of INL. After a short introduction, I will first present the crack-based sensor integration and then all the steps dedicated to the development of the portable device. During the last 15 years, the research in the field of piezoresistive transducers has mainly been focused on the use of nanotechnologies to optimize sensitivity, power consumption, cost and miniaturization. Many different approaches have been proposed in literature these past few years. Few examples are presented here on this slide. Among these different approaches, at INL we have studied 3 of them, but today I'm going to focus only on the crack-based strain sensors. The concept of a crack-based strain sensor was proposed in literature in 2014. The principle of operation is very straightforward. We start from a cracked conducting thin film, in gray here in this figure, integrated on a polymer substrate. Under tensile strain, the opening of the cracks generate giant resistance variations. Currently, the highest gauge factor presented in literature are obtained with this technology. The key point to control the sensitivity is to control the morphology of the cracks, which have a certain roughness, as you can see here on this top view SEM image. First, if you consider an ideal crack, far from reality, a crack which has no dispersion on the size of the asperities within the crack. In this case, the sensitivity curve would look like this. The resistance remains quite stable until the contact is lost between the asperities within the crack. Now if you consider another ideal case, another crack with no dispersion on the size of the grains, but with bigger grains. In this case, the sensitivity curve would look much more like this. The curve is shifted to the right, the contact is lost at a higher strain level. And finally, if you consider a more realistic case, with a crack showing a dispersion on the morphology, in this case, the sensitivity curve would look like this. To increase sensitivity, you have to increase the slope here of the curve by reducing the standard deviation on the size of the asperities. And if you want to shift the curve to the left, to the low strain levels, you have to reduce the average size of the grains within the crack. In a previous study, we have proposed to use a nanostructured thin film made of metallic nanoparticles in a brittle aluminum matrix in order to control the morphology of the cracks. The idea was to adjust the size of the nanoparticles within the matrix in order to control the morphology, the size of the grains within the cracks, in order to control the sensitivity. As you can see on this slide, we have developed a nanostructured thin film by using atomic layer deposition. We have developed some thin film integrating platinum nanoparticles encapsulated within alumina. Thanks to this nanostructured thin film, we could generate cracks with small asperities and low dispersion on the size of these asperities. Thanks to that, we could get giant gauge factors at low strain level, gauge factors which were at the state of the art at the time. From these crack-based transducers, we could also develop a MEMS demonstrator. As you can see on this figure, by simply sticking a flexible sensor on the wrist of a person at rest, we could get some resistance variations that are directly linked to the arterial pulse activity. From this nice signal, we could extract a heart rate in BPM. We could also get some physiological information with the detection of cerebral waves, and we could also have information related to the respiratory activity. You can see here a slight oscillation, which is directly linked to the respiratory activity. In the framework of the PulseSensor project, in collaboration with colleagues from the biomedical sensor group, our main objective was to push forward this concept by developing a more ergonomic system equipped with a wireless interface which communicates with an Android smartphone. At the beginning of the project, our first objective was to replace the nanostructured transducer based on platinum nanoparticles. The precursor that was used to grow this transducer was indeed highly expensive, and it was also not very stable over time. So we have decided to replace this transducer by an alumina titanium palladium stack by combining atomic layer deposition and E-beam evaporation. As you can see on this schematic, we have first grown a thin alumina layer by ALD at low temperature on a polyamide substrate. Then we have deposited our titanium palladium stack by E-beam evaporation at room temperature. And finally, we have patterned some aluminum top contact by a lift-off process from UV lithography. In order to generate the cracks, we have placed the flexible sensor in a buckling configuration between two translation stages. As you can see here on the right, on these top view Etienne images, we could easily generate 2 or 3 parallel cracks within the gap between the two aluminum top contacts at a strain level of around 1%. In order to better understand the crack formation process, we have developed some FEM simulation with Anti's software. The idea was to estimate the local strain within the gap between the two aluminum top contacts. The parameters that were used in the model are presented here in this table on the top. First, we have plotted the longitudinal strain as a function of the position on top of the surface of the sensor. We have simulated half of the structure. The gap is here at the position 0. From this graph, we could learn that there is an increase of the local strain within the gap, an increase of 0.15% strain. These results explain why the cracks are preferentially formed within the gap. The strain is indeed higher within the gap than outside the gap. Here on the right, we have studied the influence of the thickness of the aluminum top contact on the local strain. As you can see on the graph, by increasing the thickness of this aluminum top contact, we can increase significantly the local strain and facilitate the crack formation. So by playing on the thickness of this electrode, it is a way to localize the cracks and facilitate the crack formation process. The electromechanical response of these crack-based transducers was characterized in a buckling configuration. In order to avoid any effect of humidity, we have encapsulated our crack sensor with a photoresist layer. On this graph, we have compared two sensitivity curves obtained before and after encapsulation of the cracks. On this graph, you can first observe a slight hysteresis phenomenon, which is probably due to adhesion forces or to viscoelastic effect within the polyamide substrate. More importantly, you can see that we can drastically enhance the sensitivity at low strain levels by encapsulating the cracks with a photoresist. We believe that this increase in sensitivity is possibly due to compressive internal stress within the photoresist, which shifts the sensitivity curve to the low strain level, or also to the effect of moisture on the resistance of the crack. We will discuss this more in details in the next slide. From the black curve obtained for the encapsulated sensor, we could extract a giant gauge factor of 30,000 at 0.2%. Here on the right, from this benchmarking, you can see that before encapsulation, our sensitivity is lower than the one obtained with the nanostructured transducer based on platinum nanoparticles. The encapsulation enables us to further increase the sensitivity. Concerning the influence of humidity on the electromechanical response, Hong et al. Have shown in 2018 that some water droplets can be absorbed within the cracks to form current paths that decrease the resistance of the strain sensor under high humidity level. In here, we believe that a higher strain level is necessary to break this water droplet path in order to reach the high resistance state of open cracks. To verify this, we have placed a non-encapsulated flexible transducer in a cryogenic probe station. The idea was to submit this transducer to a 0.25% strain load in air and in vacuum, and to compare the resistance variation. The results of this experiment are presented on this graph. As you can see, the resistance variation is 4 times higher in vacuum than in air, which confirms that a higher strain level is necessary to break this water droplet path to reach the high resistance state of electrically open cracks. These results possibly confirm that shielding the cracks with a photoresist layer can avoid the effect of humidity on the electromechanical response. The complete system we have developed in the framework of a PulseSensor project includes the crack-based strain sensor, an analog front-end circuit, and also a microcontroller unit that wireless communicate through a Bluetooth interface with an Android application. Concerning the analog front-end circuit, we have used a 3-wire ratiometric circuit from Texas Instruments that is commonly used for a precise resistance measurement. This analog front-end circuit is connected through an ADC to the microcontroller unit, a BGM13S from Silicon Labs. Both analog and digital circuits are integrated together on the same PCB, which is presented here in the middle. Concerning the Android application, which was developed by a colleague from the biomedical sensor group, this application enables us to collect the data from the sensor and to plot the arterial pulse activity signal. And from this application, we can also adjust several parameters of the circuit. We can change the current sources injected in the analog front-end circuit. We can also adjust the gain of the programmable gain amplifier here. And we can also adjust the sample rate. On this schematic, I have presented a cross-section of the system, which includes 2 PCB. One on top in red that is dedicated to acquisition, which includes both analog and digital circuits, and another one in green at the bottom that is connected to the flexible sensor. The crack-based sensor is placed in a buckling configuration in order to adjust the base strain level in order to optimize the sensitivity under operation. The 2 PCBs are connected vertically thanks to mezzanine connectors. Here at the bottom, I have presented 2 photographs of the system. From this top view, you can see the acquisition PCB that is connected to a quite big LiPo battery. And here, from this bottom view, you can see the crack-based strain sensor in a buckling configuration that is surrounded by a 3D printed spacer, which enables us to adjust the distance between the sensor and the skin of the wrist under operation. Finally, on the right, I have presented a short video that demonstrates the successful communication between the system and an Android smartphone. On the screen here, you can see in real time the nice arterial pulse activity signal. So in summary, we have integrated cracked alumina titanium palladium stack by combining atomic layer deposition and e-beam evaporation on flexible polyamide substrate. Thanks to FEM simulations, we could better understand the crack formation process by estimating the local deformation within the gap between the 2 aluminum top contacts. We could also get giant gauge factors of 30,000 at 0.2 strain levels by encapsulating the cracks with a photoresist layer. And finally, we could demonstrate the feasibility of wireless arterial pulse activity monitoring by integrating this crack-based sensor in a complete system that communicate with an Android smartphone. I thank you very much for your attention.